So we had one Biot-Savart law that is for finding the magnetic field due to small current carrying loop, small current carrying element, and then we integrate for the entire length. And then last class we saw that if we have to find a magnetic field for a symmetrical reason, we have one another better alternative, and that is we can choose Ampere's circuital law. It's a mathematical form of to find the magnetic field. We, I think, just introduced the statement, or did we derive any result as well using
So
Ampere's circuital law?
we had done it for a hollow cylinder.
We did for hollow cylinder also. Okay, great. Ampere's circuital law is a mathematical version of magnetic field. So any loop, like suppose these are the wires, I might have taken a similar example. I1, I2, I3, I4. It's your choice, whatever shape of the loop you are taking, clockwise and clockwise, anti-clockwise later on. First, you have to choose a loop. So suppose I take a loop which is like this. This is the entire circular loop. It's not there, it's an imaginary circle which is just drawn to write the Ampere's law equation. As of now, there is no clockwise, there is no anti-clockwise. This is clear enough,
Yes, sir.
right? Now, when you choose this loop, now it's your Ampere circuital law is that line integration of magnetic field B dot dl will be mu naught times total current passing through inside of it. So if you do this integration, you have to choose one direction of dl. If suppose you are taking dl like this, so that when you take dl, what shape, what direction become anti-clockwise?
Yes, sir.
It has nothing to do with b जो है वो already decided है, that is because of the wires produce magnetic field, and that magnetic field will be already decided by the direction of the current. We cannot change, we cannot randomly assume, but this dl we can assume as per our convenience or as per our convention. But if we are integrating this anti-clockwise, the thumb will be coming out of the plane. So that means if the dl vector is integrated anti-clockwise, then currents which are coming out of the loop will be taken positive. So which current is coming out of the plane, Arnav, in this loop?
So can you explain this again? I'm confused.
Huh?
So can you explain this again?
See, on this loop, when you choose the dl, this is dl.
Yes, sir.
If we are going anti-clockwise, curl your right hand in anti-clockwise direction. Thumb is pointing up.
Upwards.
So that thumb, so basically this is nothing but a similar to thumb rule only. When you curl your right hand fingers in the direction of integration dl, thumb will be upwards out of the plane. So out of the plane direction is positive, therefore out of the plane currents will be taken positive with positive sign.
Yes, sir.
In anti-clockwise integration, out of the plane current will be positive. So in this particular example, the diagram that we have drawn here, if we are taking this integration on anti-clockwise circle, the current that is coming, the current which is coming outside is which one?
Positive.
I1 is coming out of the plane, I2 is coming out of the plane, I3 is coming out of the plane, so all will be positive. I4 is going into the plane, so that will be taken with negative sign, right?
Yes, sir.
Then we did one something for twisted loop. Those ones like there are multiple wires. This wire carrying current I1, second wire carrying current I2, third wire carries current I3, fourth wire carrying current I4. This dot and cross is showing the direction of current. So current is going into the plane in the first wire, out of the plane in the second wire, again into the plane and out of the plane. So now we are choosing the loop, twisted loop, not on the direct circle. Again, it's our choice which direction we go to integrate. Let's say we are integrating now this. I think the last class we had done it. So now this is the direction of DL. Last class it would have been opposite. I think this deliberately I have taken in opposite direction, reverse direction of the previous. You understood this diagram, Arnav?
Yes, yes, sir.
So in this particular case, when you write the integration of B dot DL, the integration is anti-clockwise. The arrow shine in the loop one, arrow is pointing in anti-clockwise direction. So thumb is out of the plane, thumb should be outwards. So that means out of the plane, current should be taken positive, but here current is going into the plane.
Yes, sir.
So I1 is negative. Likewise, in the second one, the right hand curl should be clockwise. Clockwise means into the plane would have been positive, but this current is out of the plane, so
Outside,
that will
so
be
it's
negative.
negative.
The third one,
So it's negative again.
it's negative again. Fourth one,
So that will be positive.
positive. That will be positive because the clockwise integral and thumb is pointing inwards. Current is also pointing inwards.
I have a question. In this case, why can't we make just one big loop?
Come again.
So we can we make one big loop in this situation as well, like we did in the previous case?
Yeah, why not? But this loop given for this given loop, my Ampere's law will be like this.
Okay. So they can give us a question like this. This is the loop, this is
Yes,
the.
like this question have been asked, and yes, but this loop is not symmetrical. Further, if you want to separate out B and want to calculate B, then it is not possible.
Okay.
Right? We did magnetic field formula for infinite wire, hollow wire, solid wire. That method works only when it is a symmetrical loop around a symmetrical magnetic field. And we saw that it has to be, for symmetry, it has to be passing over the magnetic field lines. So first we need to find the shape, we need to understand what is the shape of the magnetic field line, and then we will put the loop, we'll choose a loop which is exactly passing over the top of the magnetic field line. Yes, any other doubt?
No, sir.
Rahul has sent one question, so I think before proceeding further, let's solve this question because it was asked in his UT. Rahul, you got the marks as well?
No, sir.
You are not able to attend any of the Friday class. Correct?
सर मैं कल ज्वाइन कर लूँगा.
मैं कल से टाइम चेंज करने का सोच रहा हूँ, कल ज्वाइन कर लोगे. चलो ठीक है, okay.
So how will the timings change?
You know, timing, I mean, like the one batch is not able to join because of chemistry clash. So, okay, tomorrow, not tomorrow, maybe next week onwards, we'll discuss first. Friday class, some of the students are not able to join, like Pranay is not able to join, he has Fiji classes. Rahul is not able to join because Rahul attended the batch with the other batch. And I think the Friday class is also important, in fact, more important because we solve questions. Theory you can get from the books. Mostly you understand from the book, 70-80% is by reading. Question is something that you need help with. So, anyways, tomorrow we are having class. Next week we will see if. Okay, B dot L is mu naught I1. Then the application of Ampere's law, and that application is what? by using any symmetrical loop, we can determine the formula for field magnetic field due to a very symmetrical loop. So first case we did, I think two cases we have done. So just formula, right? Magnetic field due to infinite wire. Infinite wire magnetic field will be symmetrical, not for a finite wire. So we cannot use this for a finite wire. Infinite wire, we will use its magnetic field line shape. Magnetic field line is in the form of circular loop that we know from the right hand thumb rule and by symmetry. So we choose a loop which is passing over top of it and apply Ampere's law, similar to a Gauss law kind of thing. छोटा सा एक length vector which has the same direction as B. So integration of B dot dl is mu naught I and dl integrate करेंगे तो 2 pi r. Here, because of this symmetry of this loop, we can take B outside of this loop as B is parallel to the dl. B into integration of dl is equal to mu naught I and right. So likewise we did for hollow cylinder also. Hollow cylinder के लिए outside the formula will be same. Inside the wire, the current does not pass through it. Therefore, inside a hollow cylinder, there won't be any magnetic field. Magnetic field due to
Sir, can you move to the previous page?
So could you go back to the previous page?
I think it is there in your notebook, class. You can just okay. If you're noting down, it's fine. So this Sunday test will be on prep door, as it is MCQ and paper level will be slightly higher only. Yes, boss. Someone said something.
Sir, I have a question.
Yes.
How is a circular integral different from a normal integral?
What is circle integral?
You've drawn an integral with circle in the middle.
No, that is just a symbolic representation that you cannot do it open-ended, like you not start from A and end at B. It simply means if you start from A, you have to come back to A again. This circle just represent it is a closed loop integral. Now this dl integrates, dl decides it is along the length. In the case of Gauss law, it was dA. So we have to choose small surface. This integral cannot be performed from one point to another point. You have to come back to the same point again. Then only it will be, that's the meaning of this circle here. Right?
Yes, sir.
Very nice. Magnetic field due to hollow infinitely long wire. Magnetic field due to hollow infinite wire. So this is like a paper kind of thing folded in a cylinder. So it is a hollow cylinder. Only a very thin wall is there through which the current is coming out and is coming parallel to its axis. Current is I only, but that is coming out through this wall or through the circumference only. In between, there is no current. So that means it will be. So Rahul, if you are coming tomorrow, then I'll take your doubt tomorrow because that is from the previous chapter. Current is I, radius is R, and we need to find its magnetic field formula using the Ampere circuital law. बाहर किसी पॉइंट पे कैलकुलेट करेंगे इसके लिए again we have to consider a circle. For any point outside, the whole wire is inside, so magnetic field will be B out dot dl is equal to mu naught times I. The whole wire is enclosed, therefore whole current is passing through that loop. By integration, outside magnetic field comes out mu naught I by 2 pi r. Okay, similarly, if you choose a point inside, if you consider any loop, then it will be 0. Integral of B in dot dl is equal to 0, and therefore B in into 2 pi is 0. Under magnetic field होती है 0. In any hollow cylinder, when the magnetic field is passing, when the current is passing only through the surface, it will be 0 only. In between 0, outside it is inversely proportional to R. Left side, yeah. B inside is 0, outside is same as that of a wire placed on the axis. Third case is magnetic field due to a infinitely long solid wire. Magnetic field due to infinitely long solid cylindrical wire. Long solid cylindrical wire. So
Can you move back to the previous page?
done.
Yes.
Okay, so now the current is distributed on the entire length, entire surface of a cylinder uniformly. Total current is I, and that is distributed uniformly on this whole surface because now it is a solid cylinder. Current is coming out symmetrically from every point. It is uniformly distributed. Total current I, total radius is R. I mean the radius is capital R. So this current is actually distributed over a surface, और इसके लिए हम कुछ calculate कर लेते हैं current density. So the current density of this wire is current passing per unit area, and that will become I divided by pi times r square. So now again, if a point lies outside any point, the symmetry is circular only, so we can choose this as a again. So exactly similar type of loop, similar type of calculation. Outside magnetic field will be integration of B out dot dl is equal to mu naught times total current passing through it. Fine. Mu naught I इसको इंटीग्रेट करोगे तो आ जाएगा B out same calculation into 2 pi r mu naught I. So as long as we are outside the cylinder, the magnetic field formula will be similar to that of a wire kept at the axis. Just electric field में भी था, if it is a hollow sphere or it is a solid sphere, if charge is uniformly distributed and outside at every point, formula is same, k cube by r square. So outside doesn't matter. Inside now, if you choose any point, at any point inside, we have to find the magnetic field formula. Now through this loop, there will be current passing through it, though it will be less. I dash. So when you consider a point which lies inside, r is less than small r. V in dot dl will be mu naught times I dash. अब I dash को हम कैसे निकाल सकते हैं? Because इसकी radius है r. Current density means current per unit area is J. So current passing through this area of pi r square, I dash will become J into pi small r square. तो लेफ्ट में इंटीग्रेट करने पे ये b in into 2 pi r आ जाएगा. राइट साइड में सब्स्टिट्यूट द वैल्यू, सो म्यू नॉट टाइम्स j into pi r square. Pi gone, एक r से r cancel. The magnetic field at any point inside due to a solid cylindrical wire is
Sir, can
coming.
you move to the previous page?
एक सेकंड बेटा. Mu naught j by 2 times r. So inside it is directly proportional to r.
sir.
Noted, sir.
Okay, so now in this inside, magnetic field is directly proportional to small r, like magnetic field is, sorry, like the electric field is inversely proportional, directly proportional to r when we are inside a solid cylinder. Inside a solid sphere, electric field is directly proportional to r. Here inside a solid cylinder, magnetic field is directly proportional to r. So inside का formula है mu naught j into r by 2. J को हम सब्स्टिट्यूट कर सकते हैं टोटल करंट I डिवाइडेड बाय एरिया पाई r स्क्वायर into small r. Inside magnetic field is directly proportional, outside magnetic field is inversely proportional to r, so that become B versus r. Magnetic field B is linearly proportional inside, outside is inversely proportional to r. Left side में करेंगे तो भी formula same, only the direction is opposite, so it will be negative. Similar but negative. Magnetic field is maximum at surface, inside linearly. At the center it will be 0. At the center it will be 0. Understood? Magnetic field due to magnetic field due to infinitely long wire, hollow cylinder and solid cylinder. All three cases we have done with the help of Ampere's circuital law. If J is variable function changes with a small r distance, then we need to integrate this, just like we used to do for the Gauss law in electrostatics. Fine. Next is magnetic field due to a long solenoid. So what exactly is solenoid? Is a hollow cylindrical tube over which wires are bound along its length very closely, insulated wires. So it is a solenoid, a hollow cylinder. Usually length is quite large as compared to radius. That's the meaning of long solenoid. And the insulated wires are very closely wound along its length. That is the solenoid. So ऐसे होते हैं पास पास, but for the understanding purpose, the number of turns or number of loop will depend upon how much length we are using. This hollow cylindrical tube over which insulated wires are closely wound along its length is called a solenoid. और इसी के अंदर अगर हम आयरन रख देते हैं, then it become electromagnet. A long hollow cylindrical tube over which an insulated wires are closely wound. or closely wound along its length. So suppose the length of this solenoid is L and the total number of turns is capital N. So length should be at least 20 times radius, then we can apply that approximation that it is infinitely long or quite long. Number of turns per unit length. Number of turns per unit length, which is denoted by small n, is capital N by L. Now, if we try to figure out the shape, whether it is symmetrical or not, only then we can decide whether we can apply Ampere's law or we have to just use the Vaibhav law only. So every solenoid can be considered as the collection of circular coils placed side by side. किसी एक सर्कुलर लूप के लिए उसकी मैग्नेटिक फील्ड का शेप कैसा होता है? Only for one single loop. We derived the formula for this also. इसके एक्सेस पे it was like a straight. अगर ये नीचे से करंट ऊपर जा रही है और ऊपर से अंदर, and as we go above it becomes slightly curved. तो मतलब आगे जाके closed loop बनेगा like a magnet. So this will be the shape of magnetic field line due to a circular coil. This was for one, but now there are infinitely many placed side by side. So when they are placed side by side, their all magnetic field will be added to each other. And as a result, what happens is the magnetic field inside becomes like a parallel line. So in between, as it is closer, more number of magnetic field lines, closer it will be, more uniform will be the shape. That means it will become almost like parallel lines inside, and only when you start coming towards the circular part, it will become curved. So that will be the shape of magnetic field line, and then it will be like a closed loop, like that of a magnet. Yeah, so that will be the shape of magnetic field line. Now, can we say it is symmetrical? Is it a symmetrical? Symmetrical means it should have circular, it should have spherical, it should have some those type of magnetic field lines. Can we say this is a symmetrical magnetic field and we can apply Ampere's law? Yes. Is this magnetic field line symmetrical? So
And
that we
there
can
is some kind of symmetry, but
what kind of symmetry?
there is symmetry.
Which type of symmetry? Like, what is the name of that symmetry?
So if we go through the line right in the center, the magnetic field line in the center, then we'll have two symmetrical halves.
I mean, that is the mirror image. That's not the symmetry. Symmetry, what we are talking about, symmetry like here, when you choose a circle, we can take this B outside. In all the integration, that B will come outside. Why? Because the value of B is same at every point on that loop chosen. That is the type of symmetry we are looking. So we have to find such a loop at every point of which magnetic field density is same, which is obviously not true for outside as magnetic field line gap is increasing or decreasing. But if we are very close to the axis, then that magnetic field line become parallel to each other. Parallel to each other means the value become constant and will become a uniform kind of magnetic field. So uniform or constant can be considered symmetric because our symmetry involves what? we have to choose such a loop at every point of which magnetic field value is same. Got it? Only for inside this solenoid, close to the center or close to the axis, we can say that magnetic field is constant, uniform, and uniform means obviously the symmetry that we are looking, that is valid, that any loop you choose at every point of that, the magnetic field will be same. Clear? Enough?
Yes, sir, it's clear.
It's not that kind of symmetry that if you go from the center line, r distance above, r distance below, it is same. Not that type of symmetry. That's the mirror image or that's different symmetry. Magnetic field inside a long solenoid. Inside a long solenoid is uniform. Uniform का मतलब constant in magnitude. So constant in magnitude also comes under the symmetric because every point it has the same magnetic field line. Correct? And just outside the curved surface, there is no magnetic field line. So just outside it is zero. Close to the axis, it is zero. And just outside the curved surface, it is zero. Just outside the curved surface, it is zero. इस समझ में आ रहा ना why outside is zero? Because there won't be any magnetic field line closer, but it is a very long loop. So again it will appear a very diminished magnetic field line will again appear, but if you go just outside it is zero and inside it is a constant kind of magnetic field. So now if we have to find the magnetic field using solenoid, using the Ampere's second law, we can find only for inside close to the axis. For any other point, we cannot calculate. Magnetic field at the center of long solenoid. Long solenoid के अंदर, so अभी हम wire हटा देते हैं. We got how it is coming out. There is a magnetic field line. The shape of magnetic field line is parallel to each other as long as we are close to the center. This is the axis of solenoid. So इसमें जो current है वो ऊपर वाले वायर से निकल रही है ऊपर की तरफ और नीचे अंदर जा रही है. Current is like this. So likewise every thread, the current I is coming from the top and it is going from below into the plane. And so on for the entire length. Now, if we have to find the magnetic field using the Ampere's law, the first step is determine the symmetry. We got the symmetry that it is a planar kind of symmetry, but only as long as we are close to the center, close to the axis at the center. But what is the second step? We have to choose a loop. We have to choose a loop in which magnetic field is same at every point. So let's say the center. So another thing that we did, we have to choose always a loop such that magnetic field line passes on top of it. So we will consider a loop which passes over it only. And so by symmetry, we have to make a rectangle. As inside, this same length will be outside. Consider a rectangular loop P, Q, R, S, P passing through the axis to apply the Ampere's circuital law. It's not necessary you have to choose circle only, you have to choose some loop at every point of which magnetic field is same. In this case, it comes out to be a square or rectangle, anything which passes through the whose one side is passing through the center or axis. Yeah, is this clear? How we choose this to be a rectangle? Understood this part?
Yes, sir.
Understood this part? Yes, boss. Is this clear? Why we choose rectangle instead of circle in this particular situation? Is this clear?
Can you explain it again?
First step was that we had a solenoid. We understood that it is a combination of many circular loop placed side by side along the same axial position. For one loop, we saw what will be the shape of its magnetic field line. And since there are many such loops placed side by side, so all of those magnetic field lines will added up vectorially, and we get somewhat similar to this. In between, inside, the all the magnetic field lines will join and become like a parallel lines. Parallel lines means uniform. Uniform means every point is same. So any region which has a constant magnetic field can be considered as symmetrical also. The symmetry that we are looking. The symmetry is that we have to choose a loop at every point of which magnetic field value is same or constant. Right?
Yes, sir.
So if we have to choose outside is not symmetrical because density is changing. When we come on to the end, again it is becoming curved. That's not symmetrical. But yes, inside close to the axis it is symmetrical because it is like a parallel. Parallel means constant. Constant is kind of symmetrical. So on this axial position, on this axis, we have to choose a loop which is passing over the magnetic field line because we want B and DL should have a zero angle. That's why we can integrate B dot DL. So if we draw a loop or any line which is passing to the center, so we need to always integrate, consider a rectangular loop P, Q, R, S, P passing through the axis. Passing through the axis of solenoid. And now we need to do the integration. How will we do? Integration of B dot DL. Integration of B dot DL is mu naught times total current. So हमें integrate करना है B को DL के ऊपर. And that will be mu naught times total current passing through it. P, Q, R, S, P. Let's say this length is X. Current कैसे पता करेंगे अंदर कितनी है? Because each thread has same current of I. We just need to find how many number of turns are there. Number of turns inside will be small n into X because n is the number of turns per unit length and X is the length. Each turn has a current of I. Each turn has a current of I. Yes, boss. ये समझ में आ गया nx क्यों है nxi how it is
Yes, sir.
nxi. When you integrate on the left hand side, you have to open this separately. Now this circle is gone, the circle which was on the integral, because then we are doing for the whole circular loop. Now we are opening it first from P to Q, then from Q to R, then from R to S. Now in this integration, you should not put circle because these are not the closed loop. starting point is different and ending point is different. B dot dl is equal to mu naught nxi. PQ पे इंटीग्रेट करोगे तो B and DL are in same direction. B and DL are in same direction. इंटीग्रेट करोगे तो B बाहर आ जाएगा और DL का एंड B को कांस्टेंट हर जगह पे. B और DL का इंटीग्रेशन ही लेंथ आ गई, which is x. PQ length is equal to RS, which is equal to S. जब QR पे जाएंगे तो B is towards right side, DL is perpendicular. So जहां पर है वहां पे B और DL perpendicular होने की वजह से cos 90 0 हो जाएगा. और जब हम बाहर आ जाएंगे तो बाहर मैग्नेटिक फील्ड नहीं होती, वो हमने डिसाइड किया था. Outside there's no magnetic field. So half of the QR B is perpendicular to DL and half of the QR there's no magnetic field. So overall it becomes 0. RS is outside, their magnetic field does not exist. SP is again 0 because same logic. So B into X on the left side and right side was mu naught small n into X times I. X is gone, cancel. It will become mu naught and I. Yes, was this clear? Any doubt? X is gone, Rahul. Mu naught times Ni. So ये जो है small n is constant, mu naught is constant, current is constant, so that means it is a constant current. This is at the center of long solenoid. Done?
Yes, sir.
So when we go towards the end, इसको small n को क्या लिख सकते हैं हम? Capital N by L, then it will be mu naught capital N by L times I. Capital N is the total number of turns, L is the length of solenoid. जब हम solenoid के end पे जाएंगे, then only one side of the solenoid is infinite loop. So अगर हम integrate करते हैं तो ends पे जो magnetic field आती है वो center की half आती है. Mu naught and I by 2. Center से surface की तरफ जाएंगे तो total magnetic field will decrease, it become half, exactly half. Magnetic field at the end is half of the center. इसके लिए एक जनरल फॉर्मूला जो हम इंटीग्रेशन से कैलकुलेट करते हैं, अभी यहाँ पे किया नहीं है इसलिए जस्ट आई एम कोटिंग दिस फॉर्मूला. इंटीग्रेशन में क्या करना होता है वो फॉर्मूले में हम बना सकते हैं, बट मैथ्स इज लिटिल कॉम्प्लिकेटेड. सो लाइक द formula of finite length of wire, वैसे किसी फाइनाइट सॉलिनॉइड के लिए याद आता है म्यू नॉट Ni/2 इंटू साइन अल्फा प्लस साइन बीटा। अगर हम किसी भी और पॉइंट पे निकाल रहे हैं, रैंडम पॉइंट पे, किसी भी लॉन्ग सॉलिनॉइड के लिए एट एनी इनफाइनाइट at any point which is not exactly at the center, this is the formula for magnetic field in a long solenoid at a general point, not center, not end. जब हम सेंटर पे कैलकुलेट करते हैं सेंटर के लिए, तो अल्फा बीटा दोनों तरफ 90-90 हो जाएगा, बिकॉज इट इज कमिंग फ्रॉम वेरी लार्ज, ऑलमोस्ट पैरेलल। जब हम एंड पे कैलकुलेट करेंगे, अल्फा 90 बीटा 0, then magnetic field will become mu naught Ni/2 into sin 90, which is at the end. Clear? बेटा ये फॉर्मूला समझ में आया क्या? ये क्या था इधर? ये एक इंटीग्रेशन से कैलकुलेट करते हैं। इंटीग्रेशन में कैसे करना होता है? वी कंसीडर सिंगल लूप ऑफ dx और उसके एक्सेस पे पॉइंट पे हम इंटीग्रेट करके निकालते हैं। फाइनल रिजल्ट इज म्यू नॉट Ni/2 sin alpha plus sin beta, where alpha and beta are the angles formed by the ends of the solenoid. Yes. Any doubt in this part? Any doubt in this part?
No,
No
sir.
doubt, sir.
How we do the integration? I mean, how we do the apply the Ampere's law? So if we draw the magnetic field versus x graph, where x is the distance from the center, if this is the solenoid lying here, at the center it is mu naught Ni, almost constant, but when we go toward the end, it reduces to half of its value. That is this type of graph for a mu naught Ni constant for almost the entire central region, and at the end should become mu naught Ni/2. Clear? नेक्स्ट इज टोरॉइड। टोरॉइड क्या होता है? अगर हम सोलेनॉइड के दोनों एंड को आपस में ज्वाइन कर दें, then that become a toroid. Toroid is an endless solenoid, you can say, or a cylindrical tube in the form of circle, in the form of a closed ring, you can say, and over which the insulated wires are wound very closely along its circumference. So solenoid is called, toroid is called a solenoid joined end to end. A long solenoid joined end to end. An endless solenoid or solenoid which is joined end to end is called toroid. or a circular tube in the form of a ring, a cylindrical tube, joined in the form of a ring, over which insulated wires are wound along its circumference. पहले definition ज़्यादा easy है visualize करने के लिए, that अगर हम कोई सिलेंडर लेते हैं इन दिस सोलेनॉइड और सोलेनॉइड को एंड टू एंड ज्वाइन कर देते हैं, then that is becomes a toroid. So like this there will be insulated wires. इसमें current pass हो रही है and because of that current there will be magnetic field lines. Now if you remember the magnetic field line to long solenoid inside is in the form of parallel loops, in the form of parallel lines. So अभी वो parallel lines जब आपस में join होंगे तो क्या बनेगा? That parallel lines will join. It will become a magnetic field line in the form of circle like this. So now those magnetic field lines will be gone जो side से कुछ curved होती थी, because there is always another circular ring is present to which it joins. So every toroid will have two radius, one the inner R1 and outer is R2. Total number of turns is N. और इसकी जो mean radius होगी जहां पर ये सेंटर वाली लाइन है जहां पर हम magnetic field निकाल रहे हैं, the mean radius of toroid is average of R1 and R2. Mean radius R is R1 plus R2 by. So इससे जितने भी वायर्स हैं इन सबसे करंट कुछ आ रही है, सपोज उन सब में से करंट नीचे से बाहर आ रही है, ऊपर से अंदर जा रही है. सो ईच ऑफ दिस वायर कैरीज करंट ऑफ I. Right, so from every this turn the current will be coming out I. हमें चूज करना है लूप जो कि सेंटर से पास हो रहा है जहां पे मैग्नेटिक फील्ड कैलकुलेट करनी है. Magnetic field is here. We'll consider a dl vector also passing through that circle. Consider a circular loop passing through the center of toroid. And apply Ampere's circuit law for this. Integration of B dot dl is equal to mu naught times. इसमें सारी की सारी आ जाएंगी. Total all number of turns will be included enclosed inside. B into dl. B तो constant है, uniform है, हम बाहर निकाल लेते हैं. अंदर बचेगा इंटीग्रेशन केवल dl का. Is equal to mu naught times ni. Integration dl will become total length, which is 2 pi r mu naught ni B will be equal to mu naught Ni by 2 pi r. इसमें अब हम n by 2 pi r को फिर क्या लिख सकते हैं? N is total number of turns. Capital N is number of turns and 2 pi r is the total length. So capital N by 2 pi r को हम क्या लिख सकते हैं? Capital N by 2 pi r को हम लिख सकते हैं small n, which is again representing the number of turns per unit length. So कि है तो ये सोलेनॉइड ही, बस हमने उसका शेप चेंज कर दिया. So magnitude wise तो फॉर्मूला सेम ही होना चाहिए. Number of turns per unit length. Since the total length is 2 pi r. Total number of turns is n. So this will be similar to the same formula that we had for solenoid. But small n को हमने थोड़ा change करके लिख दिया. Small n is total number of turns divided by total length. Right? Toroid में एक inner और एक outer, दो radius होंगी. Yes, done. Understood this? इसमें just inside and outside. On the inside of toroid it is 0. On the outside of toroid it will be 0. The magnetic field will be existing only inside. Constant magnitude, but we cannot call it as a uniform because it's changing in direction. There, so solenoid, toroid, hollow cylinder, solid cylinder, and thin wire. All these can be calculated with the help of Ampere's circuital law because it is all of them have a symmetrical magnetic field. For a toroid solenoid, only close to the axis. For a long solenoid, we can do. Toroid is nothing but similar to that of a solenoid. Yes. Any doubt from here? Any doubt? Yes. Any doubt in this part?
No, sir.
Okay. So now we can do some of the questions from these topic. A solenoid has 5 layers of winding. Next question. This is from SL only. A solenoid of length 1 meter and diameter 3 centimeter has 5 layers of winding and each layer has and each layer has 850 turns. Each layer has 850 turns. If it carries current of 5 ampere, current of 5 ampere, calculate the magnetic field at the center. Magnetic field at center. तो उसमें क्या करेंगे, जब नंबर ऑफ टर्न्स निकालेंगे, so ये सोलेनॉइड के ऊपर, because this is very thin, so first layer, second layer, third layer, small n is the total number of turns कितने हो गए, n into 5. हर एक term में 5 है divided by L. But only this will be changed, otherwise everything is. Total number of turns for its length will be 850 into 5 divided by length. And then we have to find the magnitude at the center. Magnitude at the center is mu naught L. Correct? Solve करो क्या है? So mu naught की वैल्यू होती है 4 pi into 10 to the power minus 7. 850 into 5 divided by 1. That is 5 ampere. So that is 5. So you can test class area. That is the value of magnetic field. Right?
Yes, sir.
ठीक है. Toroid. So I'm giving this from a homework only because ये सारे formula based ही हैं questions. There are 2 exercises from SL that you have to do in the homework. 4.19 from the SL. और दूसरी है 4.27. One is on Bahasa law, another is on Ampere's law. Solve these two exercises if possible by tomorrow. Tomorrow we can discuss the doubts from here. Right? Okay. Because Sunday test will be on the prep door. So those who, if anyone doesn't know the prep door and ID and password, please message me or Srishti ma'am. We'll sort it out.
So for how many days will the prep test be available?
That test will be only for that particular 1.5 hours. It will not be live for.
Because I have my chemistry on Monday and we have 3 chapters coming in. So I have my chemistry on Monday and we have 3 chapters coming in.
Acha, okay. Well,
Is it-
see.
Can I give it on
There is
Monday
a
at least?
possibility of generating more tests. Fine. Okay then. Thank you.
Yes, sir.